Hypothalamus artificial intelligence, HI. Digital transformation powered by real-time autonomous and intelligent algorithms. Presents its artificial intelligence solutions for oil and gas state estimation. Kalman Filter. Kalman Filter applications in oil and gas pipeline systems. The image shows the chain of petroleum products. This video discusses use cases of the Kalman filter in transport of oil and gas using pipelines. Rudolf, Rudy, Emil Kalman was a Hungarian-born American electrical engineer, mathematician, and inventor. Rudolf Kalman was born in Budapest in 1930. After emigrating to the United States in 1943, he earned his bachelor's degree in 1953 and his master's degree in 1954, both from the Massachusetts Institute of Technology. Kalman completed his doctorate in 1957 at Columbia University in New York City. Kalman was most noted for his co-invention and development of the Kalman filter, a mathematical algorithm that is widely used in signal processing, control systems, and guidance, navigation and control. For this work, U.S. President Barack Obama awarded Kalman the National Medal of Science on October 7, 2009. In statistics and control theory, Kalman filtering, also known as linear quadratic estimation, is an algorithm that uses a series of measurements observed over time, containing statistical noise, and other inaccuracies, and produces estimates of unknown variables that tend to be more accurate than those based on a single measurement alone, by estimating a joint probability distribution over the variables for each time frame. The transportation system has two fundamental components, the pipeline system and the pumping stations. Estimation of the operation profile. Given the extent of a pipeline's territory, it is virtually impossible to accurately measure the main operational variables along the entire length of the pipeline. It is possible to install remote terminal units, RTUs, scattered along the pipeline, with distances ranging from a few meters to kilometers. Typical variables measured by an RTU are pressure, flow rate, temperature, and valve positions. This implies that we only have measurements with high precision at the measurement points, nodes, and for the rest of the pipeline it is necessary to estimate what is happening, based on the observed variables. This can be achieved by the physical model that mathematically explains, through differential equations, the flow of the products moving in the pipe. This is a typical case of application of the Kalman filter, KF. Given the nonlinear nature of the flow process in the pipeline, one of the most commonly used methodologies is the extended Kalman filter. System communication architecture generally implies that all reaches report to the signal concentration hub, and from there go to the control center of the SCADA system. The communication center can be a satellite or a monitoring system at the operator's offices. Mathematical modeling can be organized as follows. A real pipeline that has all the real sections, including the measuring stations installed, and a virtual pipeline that has all the sections, including the installed metering stations, and the virtual stations, where the operator wants to have measurements. Using the Kalman filter, or one of its extensions or variations, the value of state variables in virtual stations can be estimated. In this way, the profile of the operation is formed throughout the entire pipeline. State equation formulation. Brief history and future research on pipeline leaks. This section is based on the article Kalman filters for leak diagnosis in pipelines, brief history and future research. Due to operating conditions, onshore and offshore pipelines are subject to environmental loads, wind, waves, currents, seafloor movements, and earthquakes, which can lead to undesirable vibrations, stress, fatigue issues, and the propagation of cracks. In particular, the latter problem is a major source of leaks along with aging pipes, installation failures, illegal extractions, and terrorist sabotage. For this reason, in order to avoid environmental disasters, the oil and gas sectors invest generous resources for the development of robust and reliable leak detection systems. The detection and localization of leaks in pipelines may be using approaches based on the Kalman filter, considering that there are important contributions that use the Kalman filter as the core of a computational pipeline monitoring system. In leak detection systems, the methodology involves extending the estimation model of the operation profile to incorporate variables that help detect leaks. The state variables related to losses are the magnitude of the leak and its location. According to the authors of the article, without being exhaustive, the paper gathers the results from different research groups such that these are presented in a unified fashion. For this reason, a classification of the current approaches based on the Kalman filter is proposed. Then, a brief history of the use of the Kalman filter for diagnosing leaks is described, by mentioning the most outstanding approaches. Below is a table, divided into 3 images, with the works consulted by the authors. Papers with declared performance metrics. The table presents the papers that declare the accuracy indicators of the studies carried out. Leak detection. State equation formulation. Leak detection in pipelines. Case, Nor-Peruano oil pipeline. This section is based on the thesis. Desarrollo de un sistema de detección y localización de fugas basado en filtro de Kalman extendido, para sistemas de transporte de petróleo crudo, aplicado al tramo I del oleoducto Nor-Peruano. The state-owned company Petróleos del Perú, Petroperú, is one of the companies of transporting crude oil in Peru, and for this it has the North Peruvian Oil Pipeline, ONP, operating since 1977. ONP crosses the jungle, mountains, and coast, and is divided into 3 sections, Section 1, Section 2, and the North Branch Pipeline. ONP has a length of 1,106 kilometers from the northern jungle to the Bay of Our terminal on the coast. ONP has a transport capacity of 200,000 barrels per day, and plans to increase this capacity to 500,000 barrels per day. Data from Petroperú in 2021. The image shows the displacement of possible batches in Section 1. ONP elevation profile. There is a frequent phenomenon in the transport of liquid fluids through pipes, known as slack flow. This occurs in sections where the gauge pressure reaches the vapor pressure of the fluid, also known as saturation pressure, then a fraction of the fluid begins to vaporize, passing to a state of biphasic flow, liquid and vapor. It represents a problem when the elevation profile changes from positive to negative slope, resulting in a greater acceleration of the flow, and thus a discontinuity in the volume of flow transported. The infrastructure of the ONP is designed to work in slack flow conditions in the vicinity of the progressives, 323, 458 and 671, belonging to Section 2 of the pipeline. This phenomenon presents itself as a challenge for leak detection, since biphasic flow causes a decrease in the effectiveness of detection systems, based on pressure gradients. Therefore, it is necessary to have additional instrumentation. In the areas where this phenomenon occurs, also biphasic flow alters the behavior of transient pressure effects in the duct, mainly in the speed of wave propagation. During the period from 2014 to 2019, 47 contingencies were recorded. Most of the contingencies arising from criminal acts were carried out in Section I and Section 2. The section most affected by geodynamic phenomena and corrosion was Section 2. Petroperú implemented a series of measures and technological tools to prevent and predict conditions that produce leaks, as well as the use of a pipeline integrity system that is incorporated into the SCADA system. In the case of the ONP, 19 blocking valves and the installation of pressure transmitters are being implemented. The equations shown can be used to describe the equilibrium equations in a fluid flow system. The image shows the characteristics method plane diagram, x, t, in which it is the pipeline line in the space, and the time. Academic experiments. Simulations were carried out for the case of water transport, with the conditions shown in the table, taking node 3 as the leakage point located at 42.5 meters from the beginning of the pipe. To verify the operation of the extended Kalman filter, 2 methodologies were tested: Mach method, and discretized method. For both models the measurement noise was not considered. This implies that a perfect measurement system was assumed. Figure shows the response with the characteristics method, for nodes 2 and 4, nodes located at 21.25 meters and 63.75 meters respectively from the beginning of the pipeline. In the height graph, the transient behavior in time of 260 seconds is observed as a result of the leak at node 3. The magnitude of the leak does not produce a considerable change in the steady-state values. On the other hand, in the graph of the flows, it is shown that after the leakage time, node 2 has an increase and node 4 decreases, which occurs due to the dynamics of the matter balance, and by taking the boundary conditions at heights h1 and h5. Figure presents the answer for head and flow rates using the finite difference discretization method. The location of the leak is at node 3. In this solution, the flow rates show a change, while the pressure heights do not change in value, after the transient stage. This is because in the system of differential equations, the pressures at nodes 1 and 5 are considered as border conditions, and the Chi outputs in the system are analyzed. The set of differential equations, VERD, 2004, representing this dynamic is shown below. Another approach is to consider the inlet flow Q1 and H5 as border conditions. The differential equations for this case are shown below. The main difference in this approach is that the flow rate, prior to the leak node remains constant after the transient stage, whereas, if the pressure heights at the inlet and outlet are taken as border conditions, the flow rate prior to the leak node increases. According to Bogovich et al., the second approach presents a better approximation of what happens in the real world. Both solutions present similar results for the same magnitude, location, and time of the leak, and either of these two models can be used to represent the dynamics of the flow in the pipeline, and to simulate possible leaks located at any other point within its environment. The figure shows that when there is no leakage, the estimates remain stable without significant changes, while when a leak occurs, the estimated pressures and flows tend to fall, and therefore the existence of a leak will be detected. The images show the representation of the upstream and downstream constant load reservoirs as system pipeline edge conditions. Simulations were carried out for the case of water transport with the conditions shown in next table, taking node 3 as the leakage point located at 42.5 meters from the beginning of the pipe. For both models the measurement noise was not considered. This implies that a perfect measurement system was assumed. ONP Section I simulation. The characteristics of the crude oil transport, through Section I of the ONP, are modeled as a tank pipe valve tank system. The model consists of a 306 km, 24-inch diameter pipeline, with an initial tank with a 440-meter pressure head, and a 198-meter high tank downstream. The volumetric flow of crude oil is produced by a pump which supplies a constant pressure. There is a pressure height difference of 242.17 meters between the tanks. The model is simplified in such a way that it does not include accessories, such as elbows, joints, block valves, bends, etc. In addition, it is assumed that the pipe is not affected by the slope profile, since it has an average inclination of 0.0315 degrees. This means that it can be assumed as a straight pipe, making the momentum and mass balance equations one-dimensional. Estimated leak location and magnitude for different locations. By varying the leakage location for the different nodes of the Mach model, with a leakage magnitude of 5% of the total flow rate, the result of the table is obtained. The extended Kalman filter detects with a high level of accuracy the leaks located between nodes 7 to 13, with an average error of 0.47%, while if the leak occurs outside these two nodes the percentage error begins to increase. This because the dummy leak technique uses an interpolation function between these two nodes to locate the leak. This means that, in order to determine the position in nodes outside the range, the leaks must be greater than the actual leakage to produce a good estimate. This also occurs in other scenarios when the magnitude of leakage is 1%, 2% and 10%. Estimated leak location for different locations and leak magnitudes. By varying the magnitude of the leak by 1, 2, 5 and 10% for different locations, the change in error percent can be seen in table. The figure shows the estimate of the leakage flow with the extended Kalman filter for different levels of leak magnitude, where all estimates tend to be around the actual value of leak magnitude. For a location 27,000 meters from pipeline progressive. Figure shows the effect of the magnitude of the leak against the estimate of the location of the leak, As the magnitude increases, the deviation of the estimate of the location is smaller. This means that for leaks less than 1% of the total flow, the estimate will not be accurate. Kalman filter applications in oil and gas pumping stations. Kalman filter applications. PHM maintenance in pipelines. Kalman filter applications. Prognostic and health management, PHM, maintenance in pipelines. Condition-based maintenance, CBM, or prognostic and health management, PHM. Not surprisingly, the idea of efficient maintenance algorithms, originally motivated by strict emissions regulations, and now driven by safety, logistics, and customer satisfaction issues, has culminated in the so-called condition-based maintenance, CBM, program, or prognostic and health management, PHM. The PHM program/monitoring consists of two main tasks: diagnosis and prognosis, each of which has provided the impetus and technical challenges to scientists and engineers in various fields of engineering. Forecasting deals with the prediction of the remaining useful life, future condition, or probability of reliable operation of a piece of equipment based on the condition monitoring data acquired. This approach to modern maintenance practice promises to reduce downtime, spare parts inventory, maintenance costs, and safety risks. Given the importance of forecasting capabilities and the maturity of condition monitoring technology, there has been an increasing number of research and technological development on machinery forecasting in recent years. Improvement in computational resource technology has come to the aid of engineers by presenting more powerful computational resources to make some aspects of these new problems treatable. Hybrid model-based forecasting approach. The model-based and data-driven forecasting approaches have their own merits and limitations. In principle, neither approach to forecasting is superior to the other. An example of this type of model are state estimation methodologies, the best known being the Kalman filter and all its variations. These methodologies date back to the 1960s. The hybrid forecasting approach is the current one, as it integrates the merits of the two approaches at the same time, which minimizes their limitations. Thus, there is a clear trend for the integration of the Kalman filter with ANN for predictive analytics. Therefore, it is important to note that the superiority of prognostic approaches can only be specific to the particular case. Those interested in learning more about this topic can watch the video. Oil and gas PHM maintenance. Like Herbert Simon, hypothalamus artificial intelligence believes that the computer-based mathematical modeling is the greatest invention of all times. Thank you for your attention.